Dear students, in the previous class we discussed the wave nature of particle, the de Broglie hypothesis from which we could determine the wavelength of a matter wave. But when the concept of a wave nature is being attached to a particle, some serious problems arise. And the most serious problem due to the wave nature of matter is that the definition of the particle, what we understand by a particle. In our knowledge, as we understand in common sense, what a particle is. A particle is a kind of a piece of mass. Some amount of mass is concentrated at a particular position. So, a particle has a definite position and it has a definite velocity. If it moves, that means it has a definite momentum. That is our common sense on particle. But when we associate and wave nature according to de Broglie hypothesis, a matter wave, as we understand, it has certain wavelength. However small it is, it has certain wavelength, say 1 angstrom, say 2 angstrom, but still it is not a point. It has a spread in space. So a wave is spread in space, and the dimension, the size of the space it occupies is definitely the dimension of its wavelength. And so we can guess, or we can understand that when you assign a wavelength to a material particle, then you cannot confine the particle at a particular point. So, a particle that is not confined in a particular point. So, the next question comes that what is the shape of the wave? How can we express the wave? If it is a wave, it should have a function associated with it. Like we knew from our knowledge in waves that a plane wave is defined as a as amplitude sine kx minus omega t, or cos kx minus omega t, or e to the power I kx minus omega t in one dimension. If we consider 3 dimension, it will be k dot r minus omega t. We understand it. But if we want to assign a monochromatic wave in case of a matter wave, so let us assume that we have a particle which has certain wavelength lambda according to de Broglie hypothesis, and if we try to assign a monochromatic wave to the particle, say the expression of the monochromatic wave is phi xt to a to the power I kx minus omega t. But a monochromatic wave, as we know, is extended from minus infinity to plus infinity. It can be found everywhere. That is why it is a plane wave. It is extended over all space, but a particle is localized. As our knowledge says, a particle, it is not possible that you can find the particle at any point in space from minus infinity to plus infinity. If you fix a particle, it has a position. So a monochromatic wave cannot represent a particle. Now, instead of a monochromatic wave, if we consider a group of waves, that means a wave packet. You have read something on wave packets in your waves paper, waves and vibrations, oscillations and waves paper in previous semesters. So, if we consider a group of waves, then we will see it diagrammatically later. That means a wave packet which is formed due to superposition of many waves. Then the wave packet, it has a certain extent in space. The wave packet is spread over and extend in space. And in a sense, you can localize the wave packet, and we can say that if we assign a wave packet instead of a particular monochromatic wave, if we assign a wave packet to the particle, then the particle may be considered to be located within the spread of the wave packet. We will see it diagrammatically. Well, let us check it in the next diagram. We will discuss it later. So this is kind of the spread of an wave packet. As you see it, this is the wave packet, and if you consider that a particle is represented by this packet of wave, then you can say that the particle is located somewhere within this range in space. It may be here, it may be here, it may be at this point, but it is localized at a certain point in space. Now, I will discuss this diagram later. Now, if we go back to our initial discussion, so we see that a particle can be thought of being presented by a group of waves which has a certain extent in space. Instead of an infinite stretch, which is true for monochromatic wave which has infinite stretch, we consider a wave packet, a group of waves which has a definite finite extent in space. So a particle can be represented by a wave packet. Now, what does it mean actually? We will see it later. The de Broglie wavelength of a particle, as we have done it in our previous class, we have estimated the de Broglie wavelength lambda for a particular momentum p of the particle. Now this lambda has a single value. So it seems to be, well, it is a monochromatic, but it is monochromatic. But nevertheless, you have to remember that it is of finite length, because the particle has a position in space which is not extended from minus infinity to plus infinity, so it is localized. Maybe we cannot fix a particular point, but at least we can fix a range of localization, as we see in the wave packet. So the de Broglie wavelength, it possesses a particular wavelength. It is a monochromatic but of finite extent, finite stretch. And we know, we have done it in Fourier series, etc., that a monochromatic wave of finite length, it can be expressed as a superposition of infinite number of plane waves, where the frequency or velocity of the waves vary slightly from one another. That means the frequency or the velocity they vary in a range, and if you superpose infinite number of such waves, plane waves, harmonic waves, then you can form a monochromatic wave of finite length. This is actually what we do in Fourier series expansion. We do it other way around. We take a function and we expand it in terms of infinite number of component waves actually. Now the velocity of each component wave, that means each wave which is included in the wave packet, these component waves are definitely plane wave in nature. These component waves have infinite extent, and the velocity of each component wave is known as the phase velocity. The phase velocity. What is this? This is actually how rapidly its phase changes. However, we will see it later that this velocity does not carry any physical meaning. It does not carry any signal, it does not carry energy, etc. So, how rapidly its phase changes? Say you fix a particular point in space, and now the phase appears after certain time. The same phase appears due to its periodicity, same phase appears after certain time. And how it moves, how the wave moves, the particular wave gives you the phase velocity. It is known to you, in fact. However, as far as the wave packet is concerned, when the wave packet moves, the velocity at which the maximum point travels, the maxima of the wave packet, that is, say, this point. So, the velocity with which this maxima travels is known as the group velocity, and we will show it in fact multiple ways. We will show it that this group velocity in case of a matter wave is equal to the velocity of the particle. And note that the velocity, or in other words the momentum of the particle, is also measured within a range. As I told you here, that when we consider the superposition, it has the variation in frequency, also it has variation in the propagation constants or wave numbers, that is, its velocity changes, its frequency changes, and from there its momentum also changes. That is, if you want to measure the velocity or momentum, you can find that value, not exactly but within a range, and that is that range is known as is the natural error. We will read it later, and this natural error is actually, it is called uncertainty. And the same situation is also true when we measure the position of the particle. Actually, what happens if we see the function this phi, we see that it depends on, for a particular wave, this k value is fixed, this omega value is fixed. K, from k and omega you determine the phase velocity, and this k, when you superpose number of waves, maybe infinite number of waves, when you superpose and the component waves, the k values vary and the omega values vary, but the k values and omega values vary within a very short range. Not k can take any value from 0 to infinity or minus infinity to infinity. In fact, 0 to infinity. Omega cannot take any value from 0 to infinity. They vary in a very small range, certain range. So, and from k, you know, we can obtain the momentum, and from omega we can obtain energy, etc. So, when you want to measure the momentum, you see that some uncertainty is inherent in it. We will study it later in detail. And in practice, as I said it, the frequency of component waves lie within a band, in a range, and the width is determined by the de Broglie wavelength. As the de Broglie wavelength becomes shorter, the width of the band gets shorter, the range becomes narrower, and so on. Well, I have just told it other way around. In fact, as the frequency is narrower, the width gets narrower. So when the wavelength is shorter, the frequency band becomes wider. Whatever you understand that. Now, when a small wave packet, we see that a small wave packet which is composed of a small band of waves, moves like a classical particle. We can conclude it in this way. So when we assign a wave to a particle, if it is a material particle, it in particle nature, in classical concept, it should have a definite position. But when you consider the associated matter wave, then it is represented by a wave packet, which is composed of a very small band of waves. And the wave packet moves like the particle. Just you see it, I have in this figure, now I explain this diagram. This is a simple diagram showing the superposition of just two sinusoidal functions. Note that this is not wave, it cannot show propagation. This is not wave, this is only dependent on x, that means on position. In a wave there will be position and time dependence also, we will see it later. And in this case you see, just arbitrarily I have taken two functions, one is sin 10x and the other one is sin 11x. The two functions vary in their say frequency here. You know this omega, this 10 or 11, they in somewhere other relate to they relate to the periodicity. You can calculate frequency from here, you can calculate angular frequency omega from here, and whatever value it comes, we have plotted it. So fx is the superposition of two functions, and x is the displacement from, say, this is origin. So from this is 0 point, and this, if you consider this the line, then you see that there is a formation of a wave packet from this region to this region, or from this region to this region. So a packet is formed. Now if you consider the time dependence of it, you will see the motion of the packet. As simple as that. It is quite obvious. It is plotted in QTI plot. You just take in your home, use your laptop. If you have any graph plotting software, you can also plot it from Python, because you have learned Python. And just try to do or test with and try to play with such superpositions. Take 3 waves, take 4 waves, change the amplitudes here. I have taken equal amplitude here. If you change amplitudes, what happens? Just you see, and this will give you a better feeling. Now, if we, as we have said, that the maxima, it moves with group velocity. The velocity of the wave packet as a whole is actually defined by the displacement of this maxima with respect to time, which is quite obvious. So we just plotted a function psi xt, as we now denote by psi, we denote our wave function or the expression for the wave packet. Note that we have denoted by phi a particular component wave, a monochromatic wave, and you superpose infinite number of such waves to form the wave packet, which is represented by psi xt. And just at a particular time we take its plot, and definitely this capital X is the maxima, and definitely the group velocity is x prime t, capital X prime t, that means d capital X dt. So as x moves here, and the wave packet is formed, as I told you, due to superposition of plane waves, where k value changes infinitesimally. From one component wave to other component wave, there is a change in k. So you integrate over k, ak e to the power I kx minus omega t. K varies in a range dk, so you integrate from minus infinity to plus infinity to give you the function psi xt. This ak can have some other constants which relates to dimensionality. I guess you have you are exposed to, you have a knowledge on Fourier integrals, Fourier transformation and so on. In this way we see that this is a function. If this function we take, this function depends on this part. This part depends on actually this ak to the power ikx minus omega t. This depends on k, which may change, which changes. This depends on x, which also changes, and depends on time t, which also changes, and you integrate over k. Now you obtain the result of integration as a function of x and t, because k is integrated. And as I told you, it is written here that the waves in the wave packet, they have also they have their wavelength, the component waves, they have their wavelength also varying in a certain range, and in other way omega, the angular frequency or frequency, that is also therefore defined in a range, not a particular value. And ak is the amplitude of a component wave. That means ak, this amplitude that depends on k. It changes if k changes, where k is the propagation constant. I just have written it, you know it very well. K is known as the propagation constant, called 2 pi by lambda. And this equation 2, as I told you, is actually a presentation of a function. Which function? Psi xt. Is psi xt. It is just expanded or written in terms of a Fourier integral. This is a very a common thing in physics and mathematical physics. We now assume that the k values for which all the component waves vary, the k values. So as we see that for component waves k value changes and omega value changes, but this variation is within a very small range, it is assumed. And for any matter wave, this is a very relevant assumption. This is very important, pertinent, that both k and omega vary in a very small range. You see it here. So the phase velocity is definitely frequency of a component. Phase velocity means we are considering a particular wave, component wave in the wave packet. Remember it. So frequency of the component wave and wavelength of the component wave. So Bp equal to nu into lambda, and now you replace nu by omega and lambda by k to obtain Vp equal to omega. The phase velocity equals omega by k. Now you see it in the diagram here, that this upper one, this is one wave, and the lower one is another wave. These two waves superpose, as we have seen it in the previous diagram here, but in this case just two sinusoidal functions. In this case it is actually a screenshot of a video. We will see the video later. In fact, we can see it now and then we discuss. And now we see a video. We see that in the upper tier, the first wave is moving towards the right with certain frequency, certain speed, and in the second tier there is another wave which have slightly higher frequency, and when they superpose, we see that a packet is formed. This is one wave packet. As we see it, this is one wave packet which is moving towards right with certain velocity. So this is the video. The upper one is one component wave, the lower one is another, and they superpose to form a wave packet. This is an wave packet, and this packet is moving. But if you want to measure the phase velocity, you will find it little bit difficult, because say you want to measure a phase velocity, if you want to measure it, you need to fix a particular maxima at a particular point, and if you will want to see when is this moved and what time it takes to move or whatever from one point to other point and so on. Now it is a difficult task because for a monochromatic wave, and a component wave is a monochromatic wave, each wave, the successive waves are exactly similar and you cannot distinguish from one wave to other. Simply you cannot distinguish from this point and this point because it is continuously moving from minus infinity to plus infinity. You cannot distinguish one point to other point. So it is not possible to measure the phase velocity experimentally because you cannot mark at a particular point because it is indistinguishable and with other points. So this point, all these points, see, if these points move, you cannot understand that whether it has moved or it is there in its same place or as this point has come. So it takes a lot of effort, and in that case also we cannot spot a particular point for a monochromatic wave, and we cannot measure its the phase velocity. But for a group of waves, let this k for a group of waves, this velocity can be measured, and for experimental measurement is possible. Let k varies in a small range. That means a small range means there should be a mean value, an average value, where say let it be k naught, k0. Similarly, omega varies in a small range with mean at omega 0. Now, as what we have seen that means k varies within a small range, say k1 to k2. Now we, in our definition of the function psi x, we have seen that we have integrated k equals minus infinity to plus infinity, but in practice we are saying that k varies from k1 to k2, and that means from minus infinity to k1, and that means say this is our range, this point is k1 and this point is k2. So from minus infinity to k1 actually there is no wave. In fact, from k2 to plus infinity there is no such wave. So if we consider there are waves with varying k values, but for them this ak value is 0, then you can easily calculate or easily carry out the integration from minus infinity to plus infinity. As it is said here, the limit of integration ranges from minus infinity to plus infinity. We consider that ak equal to 0. When ak will be 0 if k values are away from k naught. Not if that means ak is not equal to 0 if k values are very close to k naught. Now we expand the frequency or angular frequency omega as a function of k to write it here, and as you know, it is a Taylor series expansion, and we written terms up to first order only because k naught is very close to k, and therefore the higher order terms k minus k naught whole square whole cube etc. higher order terms are neglected, and omega naught actually gives us the value of omega at k equal to k naught definitely. Now if we want to see the maxima, the variation of this maxima, at the maxima definitely del psi del x will be 0. If you differentiate psi with respect to this x, so del psi del x will be 0. So you calculate del psi del x equal to 0, which means this expression. I am not reading this expression, but you will find it. Just differentiate psi with respect to x within integration, and again you differentiate this expression, this equation 5, you differentiate it with respect to t again. Then another expression comes and you will find it like this. Now if you use this omega from its Taylor series expansion in equation 4 and replace it and rearrange the expressions, then you will see an integral like this. First integral, second integral. Because in omega you have two terms. This is the first term and this one is the first term and this one is the second term. So you replace this omega here. So you obtain separate expressions and you expand them in this form. If you look at the second integral, this is nothing but equation 5 and it becomes 0. Just check it. It is nothing but equation 5. The coefficients may be different due to 2 times differentiation, but the important terms are all same. The shape of the integration is same, and so this part is 0. So this part is cancelled. Now we are left with this term. Now if you look at this expression carefully, this integral, if you look at this one carefully, this is nothing but the second derivative, del 2 psi del x2. So this means secondary value of the second derivative at x equal to capital X, that means at the maxima. So it is non-zero because we see that maxima has a value. This maxima has a value. So this value is given by this expression, del 2 psi del a second derivative value of the second derivative, and if it is maxima, you know that you can estimate its values. So this integration is non-zero. Therefore, to satisfy equation 7, x dash t minus d omega naught dk naught has to be 0. Therefore, from 7 we obtain that x prime t equals d omega naught dk naught, and we have seen from equation 1 actually in our first equation. As we go back, x prime t is our group velocity actually. So we find out that group velocity is d omega naught dk naught. That means as the mean position varies with respect to mean k value and mean omega value varies, their ratio gives you the group velocity, and this is actually nothing but when you look at equation 4 where you expanded omega in Taylor series, you take this omega in the other side of the equation and then divide this by k minus k naught to obtain d omega naught dk naught. D omega naught dk naught is I have written it somewhere that d omega naught dk naught is d omega dk at k equal to k naught. Here we used d omega dk at k naught is d omega naught dk naught. Now d omega naught dk naught equal to d omega dk at k naught equals omega k minus omega naught by k minus k naught. As omega is very close to omega naught, then this is definitely, if you take the limit omega tends to omega naught, you can definitely write it as d omega dk. So d omega naught dk naught is it is actually quite obvious. It will be d omega dk. So the group velocity is d omega dk. And for a particle, it's for the particle, relativistic or non-relativistic, whatever, its velocity is the dE dP expression, where E is the energy and P is the momentum. So V, and if you replace E by H cross omega and P by H cross K, you obtain V equals Vg. Therefore, for a matter wave, group velocity of the wave packet denote the velocity of the material particle. So when it is possible, when you assign a matter wave according to de Broglie relation, then you find that group velocity is equal to the particle velocity. And we carry out another alternative derivation which is worked out in most of the books. We have two waves. Its parameters are omega, omega prime, or frequencies nu, nu prime, phase velocity is Vp, Vp prime, and so on. Just you take psi 1, one wave, psi 2, other wave, psi 1 equal to a sin omega t minus kx, psi 2 equal to a sin omega prime t minus k prime x. Then the resultant is psi equal to psi 1 plus psi 2. So you superpose these two waves. We have taken the amplitude of both the waves same, just for mathematical simplicity. If they are different, then also you can find out equivalent expressions. Now the resultant wave, actually, now if we see, there are two periodic functions. One is cosine function and the other is the sine function. But as the wave and k values are close, as we know for component waves, k values should be close. So k plus k prime by 2 should be close to the mean k, that is the mean k actually, and that is the mean omega. So this actually represents the sine function actually. This actually represents the wave part, the propagation. That means the resultant wave is given by the sine term, but k minus k prime is a very small term. Similarly, omega minus omega prime is also a very small term, so therefore the cos function varies very slowly, and it will give you the modulation of the amplitude. How the amplitude is modulated, that means when is the amplitude is maximum and how the maximum value modulates, that means how the maximum value changes. From there you obtain the group velocity, and that is the propagation velocity of the maximum amplitude. You obtain from this relation omega minus omega prime by k minus k prime, whereas for the wave, for the phase velocity, you obtain from this omega plus omega prime k plus k prime from the sine function. And you know the phase velocity equal to so omega plus omega prime by k plus k prime in the limit omega prime tends to omega is omega k, and the group velocity is omega minus omega prime k minus k prime. In the limit it will be d omega dk. This alternative proof is a very simplistic, very simple, but it is a particular considering two waves. But the previous approach, as we have seen it, we have seen it here. This is a more general approach, and this is of better physical footing. In fact, the previous, the first derivation using Fourier integrals for psi xt. Now we establish the relation, just dvp, phase velocity. You differentiate phase velocity with respect to k. You differentiate phase velocity with respect to k, and just carry out a simple algebra to find out that group velocity and phase velocity are related this way. And if the medium is non-dispersive, that means if the velocity of the wave is depends on lambda, then the medium is dispersive. If the velocity of the wave does not depend on lambda, then the medium is non-dispersive. So in case of non-dispersive medium, d lambda being operated on phase velocity Vp gives you 0, and which is true for light waves propagating in vacuum, and in that case group velocity will be equal to phase velocity. But note that this is light wave, not matter wave. So for light wave, phase velocity and group velocity are same. And in case of waves propagating through elastic medium, that will also happen if the medium is truly non-dispersive. Now if we want to see the relationship and what happens with the phase velocity and group velocity for de Broglie waves, the relationship remains same. The relationship given by equation number 12a between phase velocity and group velocity, they remain same, but what is the shape in case of de Broglie waves or matter waves? So in matter, as de Broglie hypothesis, we know lambda equal to h by p. If v is the velocity of the particle, m is mass, then this is like this, and you write m as the relativistic mass, where m naught is the rest mass of the particle, and your lambda takes this form. And similarly, your the frequency corresponding to the matter wave, it has a frequency, it has a wavelength, it has a frequency, and that frequency will be definitely related to the energy being carried by the matter wave. So if the matter wave carries energy E, then this E divided by Planck constant will give you the frequency of the matter wave, and then you find this relation as E equals mc square and put m as m naught by root over 1 minus v square by c square. So we see that the phase velocity is nu into lambda. You multiply this nu by this lambda, and when you do it nu lambda, you find it phase velocity into group velocity equal to c square, or phase velocity into particle velocity. Particle velocity means group velocity, that is equal to c square. So in case of a matter wave, the group velocity or the particle velocity must be less than velocity of light, and so phase velocity becomes greater than the velocity of light. It is a very peculiar thing that phase velocities become greater than the velocity of light, which seem to be contradicting with Einstein's postulates in the theory of relativity, special theory of relativity. The light possesses maximum velocity, but as this phase velocity does not carry any meaningful signal, any energy is not transported through it, no signal is being carried out by the phases. So this phase velocity is greater than c, just merely a mathematical outcome which has no serious physical significance. And if you consider the relativistic energy momentum relationship for the material particle, then you calculate that what the amount, the phase velocity expression for phase velocity. We have in this case we have seen the phase velocity and group velocity relationship, which they are connected by c square Vp into Vg equals c square, and in this case just carry out a simple algebra to find out that the phase velocity is c into 1 plus this expression. Now this expression, as we see it, is everything positive here, so phase velocity is definitely greater than c for matter waves, and phase velocity will be equal to group velocity only it is photon passing through vacuum. And in case of matter waves, phase velocity is definitely greater than c, as we see it. And in other words, if we want to see that we see that from this equation, the phase velocity of matter waves depend on lambda. You see Vp equals something dependent on lambda. In case of light waves passing through non-dispersive medium, say in vacuum, it was independent on lambda, but the matter waves, even in vacuum, they depend on lambda. This is a very important difference with light waves. As I told you before from equation 12a in the previous page, here we see, and it is also written that for a light wave in vacuum, this dVp d lambda equal to 0. That means the phase velocity has no dependence on wavelength. But from this expression we see that for matter waves, phase velocity is dependent on wavelength. Therefore, matter waves show dispersion even in vacuum. If you change the wavelength, if that means if you increase the energy or momentum of the material particle, then its wavelength changes and its phase velocity changes, which is reflected through the dispersion phenomena. Now I use this expression again, intermediate expression Vp square equal to c square into 1 plus m naught square c square lambda square by h square to calculate dVp d lambda as I see it here, and this expression is definitely greater than 0. So I now use Vg equal to Vp into lambda Vp minus lambda into dVp d lambda, and use dVp d lambda here to set this expression, which shows that definitely group velocity is less than phase velocity. So if group velocity is less than phase velocity, it will be less than C, and it makes sense, it is meaningful. Again, as Vg equals d omega dk, just you do some calculation, you try to differentiate omega and k in terms of v, where v is the particle velocity. D omega dk means d omega dv into dv dk, then carry out one certain algebra, and therefore you find your group velocity. You obtained your phase velocity here. Now you are going trying to figure out the group velocity. In the previous case here we obtained phase velocity in equation 16 for matter waves, and now we are trying to figure out group velocity for matter waves, which finally come out to be d nu dv into 1 by ddv of 1 by lambda. So we differentiate the frequency with respect to particle velocity and differentiate 1 by lambda with respect to particle velocity. And in previous page we estimated the frequency and the frequency as a function of particle velocity, and here we have seen that wavelength as a function of particle velocity. So we use the expressions to calculate d nu dv, this one, and again this one. So we obtain, using the expressions, just to do the mathematics, very simple mathematics set, only differentiation, the group velocity comes out to be the particle velocity. This is again verified. We have already seen it before. So we can say that the matter wave represented by a wave group, the matter wave which is represented by a wave group, moves with the particle. Just before we end, we can find out the de Broglie relation from the relationship between group velocity and phase velocity. It is actually the other way around. We use the concept that the group velocity is equal to the particle velocity, and then we use the expression that group velocity equal to d omega dk. Now use our omega equal to 2 pi nu and k equal to 2 pi by lambda. So you differentiate nu with respect to lambda, and so on. All the expressions are given, and what happens that you can do it in as in the previous case also, d nu dv into dv d lambda. So this in some way the expression is carried out here. You finally end up, after certain very elementary algebra, that beta equals this expression. So beta equals v by c. You have v equals this expression here. Now take one c in the denominator to obtain v by c. So it will be beta, and here it will be m naught into c, this c, and the lambda square by h into this expression. Now you integrate it. You cancel this beta from both sides. Take this d lambda in the left side by lambda square. So separate lambda part and beta. Beta means the velocity part actually, as beta equals v by c. So lambda part in the left side and velocity part in the right side. You integrate to obtain this expression. This is a very elementary integration. I have not carried it out. I have just written the result. So 1 by lambda equals this expression, and replace beta by v by c to obtain c into beta equals v. So this is m naught by h into v by root over 1 minus v square by c square, and this m naught by this part, the m naught by root over 1 minus v square, it gives you the moving mass m. And for the evaluation of this integration constant a, we see that we set a equal to 0. But when it is possible? It is possible if when v tends to 0, lambda tends to infinity. That means v tends to 0, that means beta tends to 0, lambda tends to infinity, then a will be 0. This is one way of measuring, and we will check it that it is correct. So using this, you find 1 by lambda equal to mv by h, lambda equal to h by p, and it shows that if p is 0, that means the velocity is 0, then lambda is infinite, which is correct, and it gives us back the de Broglie relation between the wavelength of a material particle and the corresponding wavelength of the matter wave. So we end here today.